You have to know the formula for the number of derivatives, or you have to be able to rederive it. But I certainly wouldn't want you rederiving it because that's going to use up your time. So make sure you know the formula. So let's recall. D sub n is equal to. We derived this using the subtraction idea as well. It's just inclusion exclusion. So you take the total number of permutations of n objects, that's n factorial, and then you're going to end up factoring it out, and you're just going to subtract away from that n factorial, right? So it's factored out 1 times n factorial, and then minus, it's 1 over 1 factorial, plus 1 over 2 factorial, minus 1 over 3 factorial, alternating sum, right? And then at the end of the expression, you can figure this one out on the fly. The even numbered terms should be with plus signs. The even factorials, so the even factorials should be with plus signs. So on top here, it's either plus or minus 1, and if n is even, we want it to be plus 1. So that's the expression. Okay? Burn it into your minds and keep it there for at least a couple of days. That would be good. So, Peter, this was your idea was to use this, right? So what am I going to do next?
So we apply that formula to the b sub n minus 1, the arrangement of n minus 1 items, and the arrangement of n minus 2 items.
Okay, that's a classic thing. You want to prove a formula. I would always start with the harder side, the more complex side. So we start with the right side, then we can try to add those things together and see if it gives us d sub n. Okay, so we recall the definition, which is one reason I wanted to do this problem, was just to put the formula on the board again today. And then we're just going to write down n minus 1 times dn minus 1 plus dn minus 2. We're just going to write out what it is. So it's n minus, this is going to be a little messy, by the way. You need a little bit of room on your paper. So dn minus 1 is n minus 1 factorial times 1 over, 1 first of all. 1 minus 1 over 1 factorial plus 1 over 2 factorial minus dot 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 plus negative 1 to the n minus 1 over n minus 1 factorial. So it's that whole thing. That's d of n minus 1. And I have to add that to d of n minus 2, which will be n minus 2 factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus dot 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 plus negative 1 to the n minus 2 over n minus 2 factorial. And then I need another bracket. Okay, so we write all that down. Whew. Let's see. Does anybody see any algebra I could do? Maybe somebody besides Peter who's done everything so far. Huh?
Pull out the 1 minus 12 plus 1 all the way to
Pull out this thing?
where is that number?
Like, algebraically, I'm not sure how you could do it. The way things stand right now, I don't know what you mean by pull this out. This isn't the same as this, you know. And they also have different things out in front of them, too. So it doesn't quite work. Got an idea?
Pull out n minus 2 factorial.
Okay, good. So there's n minus 2 factorial here, and there's n minus 1 factorial here. So those two expressions have almost all of the same factors, don't they? So I'm actually going to do that. That's actually the next thing I wanted to do, which is to take out the n minus 2 factorial and pull it way out in front. And when I pull it way out in front, I'm actually going to be able to combine it with n minus 1. And when I take n minus 2 factorial and I combine it with an n minus 1, what do I end up with? N minus 1 factorial. Now, admittedly, that is not what I'm hoping to end up with eventually. Eventually, I want to get n factorial out front, but at least I've started to make some progress here. So I'll pull that all the way out, and then let's just see what we're left with. On this term, I have not pulled out the entire factorial. I only pulled out n minus 2 factorial, right? So that leaves me with an n minus 1 times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus dot 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 plus negative 1 to the n minus 1 over n minus 1 factorial. So I have that. And then on the second term, I have pulled out the entire factorial. So 1 minus 1 over 1 factorial plus 1 over 2 factorial minus that. Negative 1 to the n minus 2 over n minus 2 factorial. So something along those lines. So far so good? See something you want to do?
Yeah.
What do you want to do?
term that come before that first. So we end there's an n minus, no, that first term?
This one.
Yes.
Uh-huh.
There's an n minus 2 factorial that come before that. And then we distribute the n minus 1 through, and have similar term as well again.
Okay, so if, let me just say it this way. That, you're absolutely right. If this part in brackets was the same as this part in brackets, admittedly it's not, but if it was the same, if this bracketed piece was the same as this bracketed piece, then think about how many of them you would have. You have n minus 1 of them here, and you have 1 of them here. That's a total of n of them. And if there are n of them, you could take the n of them, pull the n out, and combine it with n minus 1 factorial and make n factorial, which is exactly what you want over there. That's all hypothetically if these two things in brackets were the same. They're not, but you know what? They're almost the same. There's just one extra term right here. But I can always just stop short of that last term and say, well, let's not take this entire thing. Let's only take all of the terms up to this one, and we'll take it out of both of them, and there'll be n of those, right? So that's exactly what that's exactly what we want to do. N minus 1 factorial. We're going to have n copies of 1 minus 1 over 1 factorial plus 1 over 2 factorial minus plus, and we're going to stop at n minus 2 factorial on the bottom because that's as far as the common terms go. Now we're not done. We're not done because there's something that didn't get factored out into this one giant term, which is this one right here. Yeah? Which goes with this n minus 1, by the way. So we have n minus 1 times negative 1 to the n minus 1 over n minus 1 factorial. Okay, so we have all that. And now, I can distribute this together, right? I'll make n factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus plus minus 1 to the n minus 2 over n minus 2 factorial.
How can you pull that out if there's no n in the second?
No, I'm not done yet. Let me finish. So this is n factorial times this thing, and then this n minus 1 factorial from right here has to be distributed to this piece. And it leaves me with n minus 1 times negative 1 to the n minus 1 over n minus 1 factorial. Let me just make sure I've done that right. And we're looking on the other board over there is what we're trying to get. I think it's right so far.
Wait,
Now-
I'm really confused on how you pull out the n minus 2 factorial. Then we get input n minus 1 factorial.
So this guy right here and this guy right here have almost all of the same terms. In fact, what you can do, this n minus 1 factorial, if you prefer, you can think of it as n minus 1 times n minus 2 factorial. And now I'm pulling that out along with that. I'm taking the circle things and pulling them out in front, and it's being combined with n minus 1 to make n minus 1 factorial. We're playing with factorials here a little bit. So this thing here was n minus 1, which we started with, times n minus 2 factorial. This is equal to that. So we pulled out n minus 2 factorial, combined it with the n minus 1, and that gave us n minus 1 factorial, and then this was what we were left with. I guess I'm missing a bracket here.
Yeah.
Okay. And then I kind of pulled out the common piece here with all of this and factored that out, and there were n minus 1 of them here and 1 of them here, so that makes n of them. And then there's just this leftover term that wasn't part of what I circled, which is just this piece. Okay, so this is what we have. Look where we're trying to go. What's the difference? This d sub n goes all the way to negative 1 to the n over n factorial, but our expression on the first part here stops too soon because it stops at the n minus 2 term. We have to hope that this leftover piece at the far right side is exactly what we need to get the rest of the terms that we didn't get in the answer that we're looking for. And I think it'll be pretty easy. Okay? Let's try it. First of all, I'm going to cancel n minus 1 factorial from the top and the bottom. And then, well, what terms am I actually missing over here? Let's see. There's the term right before this one, right? These two terms, right? Well, what is this term? Don't forget it's being multiplied by n factorial. So n factorial over n minus 1 factorial is actually just n times negative 1 to the n minus 1. So that term is missing from what we have. And then the very last term is just negative 1 to the n. You see that? Because negative 1 to the n, it's divided by n factorial, but it's also multiplied by n factorial. So it's just minus 1 to the n. So the last two terms of the d sub n formula are exactly this. Right? I know we've been at it for a while, so people are getting a little tired. I just want to stop and make sure. All I'm trying to say is if I FOIL this out and multiply the n factorial through, and I look at these last two terms, they are precisely this and this. And my question is, are these last two terms the same as what we are missing, the part that we have right here?
Yes.
I hope so. If it's not, I screwed up. So it is, isn't it? It is exactly that, because you can take negative 1 to the n, right? I can take negative 1 to the n, and I can steal one of those negative 1s by changing this sign. Right? And now I can factor the negative 1 to the n minus 1 and give myself exactly this. So you see, this thing here, this expression that we have is exactly n factorial times, I'm just going to go do a big ditto here, right? Plus n factorial times the last two terms over there, which are minus 1 to the n minus 1 over n minus 1 factorial, plus minus 1 to the n over n factorial. And that's simply rewriting this thing right here. So then it equals d sub n at that point. Now I'll be honest with you about something. Do you want to ask a question? Go ahead. Okay, good. That's where I was going. That's what my comment is going to be about. So probably this wouldn't be the best test question. The reason I say that is because it's a lot of kind of algebra manipulation and so on. Why did I ask you to do it right now? It's because, well, first of all, the review session questions, I don't have to worry quite so much about what I'm asking, but I wanted to get the d sub n formula up there for everybody to see it again. And I wanted to make sure you guys can kind of do some manipulations with factorials. It doesn't hurt to be a little bit fluid with that. But yeah, this is kind of a long-winded solution that's not particularly like exciting conceptually. It turns out that that formula can be proved without any of this stuff, and we can always just blame Peter for this approach. Suggested the formula approach. No, this is the way I intended people to do it. But it's also possible, what you're doing is you're explaining derangements of n objects in terms of derangements of less objects, right? And it's what's called a recurrence relation, and that's actually chapter 7 of our book. So in the very next chapter, we're going to learn how to count things by taking the problem we're trying to count and break it into smaller problems and solve those instead. Or you can think about this, maybe you guys want to give me a combinatorial proof.
No.
I was gonna,
No?
I was gonna ask if that was possible.
It is actually possible. Here, I'll start it for you. The first slot can be anything except a 1. So I have n minus 1 choices. Which is what you see right here. Right? And then from there, so you write, because you're writing down a derangement. Remember, that means a 1 does not go in the first position. So this number right here that you start with has to be a 2, 3, 4, 5, 6, up to n. There's this many choices. And then you can say, well, suppose it's a 2. Right? And then the question is, how many ways will there be to finish this string? And I claim there are this many. And that you can think of those remaining the number of ways of finishing the derangement in 2 cases. One of which gives you this number, and one of which gives you this number. Okay? The one that gives you this term is pretty easy. Basically, you just say, well, you put a 2 here, so then when you get to slot number 2, put a 1. And then how many slots are left? N minus 2 slots, you just need to derange those slots with the numbers from 3 to n. And then you'll have a full derangement of the whole thing. So that's one case. And then the other case is, well, what if this is not a 1? So you kind of break it down that way. I don't want to go into the whole stuff. But it is possible to get a combinatorial proof for that. Okay. You want me to do number 4 on the sheet? Okay, sure. Number 4 on the sheet. I will do it. And then I think I'll probably quit at that point. I'll let you guys. There's like 1 or 2 more problems on here, but eventually I need to shut up and let you guys go solve these problems on your own. Study for yourself a little bit too. So number 4 says, prove. Number 4, prove. Out of 217 integers, we can always choose a subset of 13 of them such that the difference of any 2 is a multiple of 18. Multiple of 18. So, before we go any further, do people know what topic this has to do with? You see the divisional principle there? Yeah, see, the idea is that when you divide by 18, what are the possible remainders? 0 through 17, right? There's 18 possible remainders. So there are, is that what you were going to say, Lisa?
Yeah.
There are 18 possible remainders. And we can make those possible remainders into the pigeonholes, the boxes, right? Viewed as boxes. So we would have a 0 box, a 1 box, a 2 box, all the way up to an 18 box, right? And
Wait, 17.
17. 17. And one thing with this pigeonhole principle, if you're going to use it, make sure you're explaining how you're putting pigeons into boxes. So the idea here would be you take each of these 217 pigeons and you put it into a box by doing what? Exactly, you take each number in this list and you figure out its remainder. It's also called a congruence class if you've taken abstract algebra. So, place numbers in boxes according to their remainders upon division by 18. So you just divide each of them by 18, keep writing down what all of the remainders are of all of those calculations, and you'll have 217 objects in these boxes, right? So then we would like to show what here? That in some box, what would we like to guarantee? What are we trying to prove?
That there's at least 13.
That there's at least 13 of them that are in the same particular box. So you see, it may not be the 0 box necessarily, but if I can get 13 objects into this box, right? Whatever. 13 things into that box, then that means that the differences of those numbers that you subtracted, if two numbers both have the same remainder when you divide by 18, then when you subtract them, you get a multiple of 18, don't you? So like 21 and 39 both leave a remainder of 3 when you divide by 18. When you subtract 21 from 39, you get a multiple of 18. You actually get 18. Okay. It's just a simple example. Okay, so now we have this, the idea was to use the strong form of the divisional principle. So it just said, if you remember, if we put, so use, I'll just state it here, corollary 3.2.2 in the book is the strong, sort of the strong form of the divisional principle. If we put r times n minus 1 plus 1 objects in n boxes, then at least one box has at least r objects in it. So the way you use this corollary is you reverse engineer it and you say, what do I want r to be? And then you figure out what does n, how many objects do you need in order to do that? We already know what n is. N is what here? How many boxes do I have? 18, right? What do I want r to be? R is, we would like there to be at least one box with at least r objects in it. So what do we want the r to be? 13. Okay. So then this is telling you how many objects you actually have to have. So it would be 18 times 13. Oh boy. You know how I do 18 times 13? I do 20 times 13, which is 260. And I realized, oh, I counted 13 2 times too many. So I subtract 26 from 260. 260 minus 36 would be 13 times 20, 260, minus 26, thank you, is 234, and then plus 1, so...
But isn't that 13 times 17?
Oh, yeah, I was trying to figure out why I was not getting the right answer. Hold on, so, yeah, I want to take r times, 13 times 17, so that's 260 minus 39, right? Oh, just don't worry about it. You guys don't like my method, I hate that one. It's too difficult for 3 o'clock in the afternoon. So 222, that's not right. 13 times 17, I just said by the strong form of Mitchell. 217 objects. Is that enough objects? So, oh, no, I'm doing this backwards. It should be, I'm sorry, the worst case scenario would be if there were 12 objects in every box. So that would be 18 times 12 objects that you could have, so that there's not 13 of them in any box, right? So with whatever this number is, if there's 216 integers, you could have 12 of them in every box. So you have to add 1 to that to get 217. So
So R is in boxes.
oh, I know. Oh, no. I know what I'm doing wrong. Something's wrong here, and it's because the formula is not right.
You switch
This should be,
them.
yeah, I got my N and my R reversed. I'm sorry, guys. This should be R minus 1 times N. Yeah, so these numbers were right over here that I wrote down before. N is 18, that's the number of boxes. And the R is the number that you want to have in one of those boxes. But I had the N and the R switched, so I was trying to take 17 times 13, and I should have been taking 18 times 12 and adding 1 to that. Okay, so it does work. You actually don't need to cite this result here necessarily, because you can just simply say, well, with 18 times 12 objects, which is 216, you could have only 12 objects in every box. So in the worst case scenario, it would take you 1 more object than that to guarantee 13 objects in a box. So that would be 217 objects that you would have to have for that to happen. Okay, sorry, I kind of fumbled that up at the end. It's just this, I've written down this formula wrong. Does that make sense?
So what is our final conclusion?
So place numbers in boxes according to their remainders upon division by 18. Well, it's just basically that we're done. So by corollary 3.2.2, with n equal to 18 and r equal to 13, we get the desired conclusion. There's nothing else. You don't. The corollary states what you want to say, so you don't actually have to say it if you've already written down the corollary. Yeah.
So we don't need to write like, if there's at least 13 objects in one box, then that means that there are at least 13 integers that are multiplying 2 of them are multiple of 18.
Oh, just the part about numbers being in the same boxes mean,
Yeah.
okay. Oh, I see. So we get the desired conclusion that some box, I'll go ahead and add that, good point, has at least 13 numbers in it. This means any 13 of these numbers